Hey guys, BuildZoid here, and today we're just going to be taking a look at taking a look at and talking about some stuff I've been messing with my GTX 780 Ti's. So I'm finally making progress through the backlog of GPUs. Unfortunately, I've bought like way too many new GPUs, so I've actually not really made any progress. I've made like one step forward, and oh well, okay, no, what's more accurate? Picked up like three steps forward, three steps back. Let's put it that way. So I've been messing with my 780 Ti's. This is my 780 Ti. This is the 780 Ti classified I have. Yeah, it's been now in my possession for far too long, so it's become a Zoidified for a few reasons. And this card has quite a bit of sort of story to it. So I got this card as just a bare PCB from a fan of the channel. Well, it came with it came with this base plate right here. Now, it doesn't have this base plate because I don't know why it doesn't have this base plate. It has a different base plate, but not this one. So, yeah, but it came with that base plate and just a bare PCB, no heatsink. So, the guy also sent over a 780 Ti DirectCU 2 that had a cracked PCB. Now, that 780 Ti DirectCU 2, I've also been messing with that card in the last few days, and I got that card working, because originally it came to me and it was totally non-functional, and I got it working again, and then recently it stopped working completely. Basically what started happening with the card is, like, it would not be detected by the motherboard properly. And normally, if you just jostled it around in the PCIe slot a bit, it would start working again. So you'd like tweak the an angle at which it's sitting in the motherboard, then tighten down the mounting hardware again, and it would start working again if you did that. But yeah, at this point, I can't, like, whatever was previously like the perfect angle to have the card at in order for it to function. Yeah, that's no longer the case. No matter how hard I try, that card just motherboard just acts like it's not installed. The whole thing fires up. All the VRMs still turn on, so all of that still functions. All the voltages are in spec, but the card is not recognized whatsoever. So I guess at this point the crack has taken, and I even tried to do things like reduce how much PCIe bandwidth the card has. So like I cut it down from 16x to 8x because the crack is all the way at the end of the PCIe slot, and I was hoping that would fix, like, that would be like a sketchy workaround, but no. I just can't get the card to boot up whatsoever, and there's no obvious, like, visible damage on it, so yeah, I'm really not sure why it doesn't work, but it doesn't work. So at this point, it's basically just being like, at this point, I consider it spare parts because I'm pretty sure all the memory on it works. The core should also be in perfectly good condition. The VRM works. The PCB is just completely trashed. So currently it's kind of like I'm thinking of it as basically a donor card for this card right here, which is another 780 Ti. So we'll get to this card soon. So this 780 Ti, this one right here, this classified, so this is the one that I got sent. Huge thanks to the guy for sending it in. But since it was just a bare PCB, eventually I was like, well, I want the original classified heatsink for it because I think this is a pretty cool looking heatsink. I can take the stickers off, right? So yeah, if I want it to look stock, it can look stock. So basically at some point I like a couple days ago, this thing was like perfectly restored, cleaned, clean PCB, clean heatsink. Though there is one issue with this heatsink. There's a few loose fins in the end here, so I actually ended up putting also, because of the way this heatsink is assembled, there's like a screw that goes right under this highlight piece right here. There's a screw that goes through this area. That's under it, and I don't want to deal with that screw. So before that screw, like this screw over here, showed up, I actually got the shroud to stay on the heatsink with that bit of wire over here. So yeah, this thing is like restored to like BuildZoid standards, not proper restoration standards. Anyway, what's going on with that screw over there is that basically there's a bunch of fins in here that are loose. And they would rattle like crazy if you put the fan to anything above 80%. I can deal with like fan noise and wind noise. I'm fine with that. Rattling fins get on my nerves. So yeah, I put a screw through those, and that's just like, I'm lucky that EVGA puts all these like vent holes through their fins. I guess the idea is that since the like there's a bunch of fins in there, that fan technically, like, I don't know if you can, yeah, that doesn't show, but like there's a bunch of fins in this section of the heatsink that obviously don't get any airflow if they were just, you know, solid fins. So they have some holes in them, and the fan basically sort of chucks air through them sideways. But anyway, if they didn't have those holes, then yeah, this fix wouldn't work, and I'd have to like do something else to the fins. But they were rattling. Put a screw through them. Now they don't rattle anymore. So that's what's going on with that. So yeah, it's not not like perfectly restored, but it does at least have the original shroud, and it looks like a classified, as long as you don't look at this end of the card, which nobody really pays attention to that end of the card. So yeah, oh yeah, and there's actually, I'm not sure how easy that's going to be to show. Yeah, okay, you can't see it, but there's a power limit removal mod on this thing. So is it just me, or is the white balance just completely messed up right now? It's fine. It might just be because I'm using a different monitor than usual. So yeah, that's the current state of like this card. So it got this heatsink, and it got that heatsink from this card, which I picked up on eBay. Now this card, I picked it up on eBay as dead. It works now because of that right there, but I picked it up as dead, and I think it was listed as like no display output or something. And ultimately, I just wanted a heatsink. So I was just like, ooh, cheap 780 Ti classified, that's dead. Steal the heatsink, bolt it onto the good card. And then, you know, since this was dead, I was like, well, what's the word? Like, I can either chop off the VRM or I can try fix it. And there's no real damage on this card that you could like look at and go like, oh yeah, I can repair that. Because what's actually wrong with this thing is, well, what was wrong with this thing, and it's still broken, technically speaking, is basically what tends to happen with these very large, high power consumption dies of silicon is that they have a tendency to thermal cycle themselves to death. Now, some of these chips have it really, really bad where it's just like mass failures very, very quickly. But even like relative, like you don't hear about like 780 Ti's dying. Like most 780 Ti's that die have the VRM blow up. Okay, that's at least what I've kind of noticed is like the memory VRM blows up, vCore VRM blows up, and it's mostly the reference cards where just the VRM goes because the reference NVIDIA reference GPUs, if you go far back enough in time, they get steady. Like as you go back through time, NVIDIA reference GPUs get steadily worse in terms of build quality. And by that, I don't mean the heatsink. I mean the PCB. And the 700 series wasn't exactly the height of build quality by any stretch of the imagination for NVIDIA cards. So yeah, there's a lot of like reference 780 Ti's out there that are dead where I assume it's probably just blown up VRMs. But the other thing that tends to happen, and like 290Xs get this a lot, and just all kinds of high-end cards get it. Like GTX 480s are kind of notorious for it. Is that basically the chip will thermal, like as it thermal cycles, so as it expands and shrinks and expands and shrinks, it breaks the connection between the die and the substrate. So that's the smaller green PCB around the actual chip. And the thing is, you can actually thermal shock it back to life if you're lucky. So what I did with this card is I heated it up to 130 degrees Celsius for about a minute. Actually, I'm not sure if it was even a minute. It was maybe a couple seconds. I don't remember that much of the procedure. And then I reassembled it, put it in the computer. Bam, we have an image, and it actually runs benchmark. So that's great. So that right there is a repaired GPU. Really, this is the equivalent of like hitting a car engine with a hammer and then going like, look, it runs now. Like, yes, it might run, but you haven't actually fixed anything. You've just hit it with a hammer and got lucky. So this is a similar situation where, you know, this will probably stop working again, but I just don't know when it will stop working again. So that's That's kind of the issue here, but because I have that other 780 Ti, which I am convinced has a perfectly functional GPU core and a perfectly functional set of memory, if this thing dies again and I can't heat it back up to life, thermal shock it back to life a second time, then I'm stealing the core. Then, the goal is basically to take the 780 Ti core off of the DirectCU 2 card and whack it onto this card, especially because the core on that other card is probably way better than the one on here. Though the funny thing about that DirectCU 2 card is it also had like performance issues. Like before it even died, I already was having issues with it just scoring really, really low in benchmarks. So I'm not entirely sure what's up with that. Or it might be just no, it was just scoring low in general. So yeah, that's kind of interesting. But hey, if I whack the core onto a classified PCB, it should perform like a classified, right? The PCB doesn't care what core's on it. So, yeah, that's kind of the plans. And other than that, with these cards, I ran into a bunch of issues when messing around with them. Turns out there's a BIOS for these that is completely busted, like doesn't work whatsoever. Because basically, if you use that BIOS, the cards cannot clock above like 1200 megahertz. Just if you raise the core clock above 1200 megahertz, no matter what voltage you're running, no matter what power limit you're running, you cannot finish benchmarks above 1200 megahertz on that BIOS. So luckily, I figured that out eventually. Not before I power modded both of these cards because, yeah, so this has a power limit removal, that has a power limit removal, but yeah, eventually I figured out it's actually just a BIOS issue. So now this has this has a proper BIOS on it, that has a proper BIOS on it, and just for future reference, it's just like, yeah, if you have a 780 Ti classified and you're having issues with overclocking, you probably have the wrong BIOS. I'm gonna maybe look into figuring out which BIOS is the good one, and then I don't know, making that a resource available somewhere. Maybe like the r/overclocking wiki or something. I'm not really sure. Anyway, so yeah, eventually I figured out that it's BIOS issues, and that's kind of that. So that's this card, and yeah, this card gave its cooler, and actually the base plate from this card is on this one. Also, the cool thing about this power limit mod that I have here, the power limit removal, is just it actually clears the stock cooling system completely. So you can see that it clears the base plate just fine, because it doesn't get anywhere near it, and yeah, that's just kind of neat that you can run and this card has that same mod, and it obviously has the full heatsink assembly. So anyway, I just like to be able to cram, it's like, it's not hard enough to do vault mods. You also have to cram them in as tight a location as possible to make it really interesting. So let's take a look at the back of this thing, because, well, I had this card for far too long and I was very bored. And that's how it ended up with this. Zoom, more zoom. There we go. Wrong direction. There we go. So that is what's going on with the core on, with capacitors on the back of the core here, and I'm not sure how much more I can zoom in. Okay, yeah, that's the limit of the camera, so you know what, we'll just pull up a picture, because that's going to work far better. So where is it? Bam! Ta-da! Oh god, it's huge. But if we wait. Oh no. Oh no. Why do I always do this? Oh, there we go. I can scale it. So here we go. So there's a picture of the back of the core. And believe it or not, this actually helps the card clock higher. Turns out that most of the capacitors around the GPU core, and I just realized I don't have my multimeter right here. Oh, there it is. Got it. Okay, so I'll show you later, but basically what you can see on the screen right now is that, yeah, so some of the capacitors are obviously like stacked up on top of each other, like on top of the existing ones. Oops. No, that's not what I wanted to grab. I wanted to grab this. There. So if go at the side like that, ow, just think I cut myself with the fin stack, but zoom out a bit. Yeah, so you can see that like the big 47 microfarad multi-layer ceramics, those are stacked on top of the existing multi-layer 0805 ceramics that the card comes with stock. Now, I assume those are probably like 10 microfarads, so yeah, I've pretty much quadrupled what's sitting there. Well, actually more like increase, more like 5 times increase, not just quadrupled. I don't know what you would say for 5 times increase. Anyway, so those are so some of them are stacked on top of each other. Some of them are just sitting next to each other. There's some like, and the thing is, this is really hard to do. Like, that's my finger, and like the smallest capacitor down there is like like this guy over here. Right, like this right there, that is an 0402. So that right there, there's a couple, like there's this one, and then that one, and yeah, there's just a ton of really little ones. And this actually helps the card quite a bit. So, and actually, the worst part about this is because I was bored and my test procedure is super accurate, which it isn't. Basically, I actually installed the 2 really large 1200 microfarad Nichicons before I did all of the multi-layer ceramics. So I'm not sure how much impact these had. And I think I actually installed this one, like this cap over here, so this 22, and that 22, along with the 2 1200 microfarad caps. So those were all on there before I did all of the, like, really the 4.7 microfarad 0402s, and the 47s. And the reason why I actually ended up doing this is because I was messing with the 780 Ti Direct CU2. I added a whole bunch of multi-layer ceramics directly behind the core on that thing, where there's actually more space to work on that card because it doesn't have quite as an elaborate set of, bypass capacitors right behind the core. That one has a slightly more barren area behind the core. And so there I added a whole bunch of capacitors, and that thing was clocking like crazy. Like, the performance sucked, but the core clock went really, really high. So I was like, so either this thing has a core made of gold, or the cap mods actually did something. And so I whacked the caps on the classified here, and this actually helped. So I don't know how much impact the big fat 1200s had, and some of the 22s had, but with all of this added on top of that, I picked up another 13 megahertz. So if these had any impact, which 13 megahertz, like, it's not a lot, but it's more than, you would expect. And there's maybe a chance that it would have been 26 megahertz if I had actually done a proper procedure where I first tested the card completely bone stock and then started adding capacitors instead of just instead of like adding a couple and then adding more and then going like, oh, more is better than slightly than whatever I had on there before. So but this did help. And what else did I want to mention? Also, the annoying thing with Kepler is Kepler actually has a restriction on how much you can step up the core clock. So this thing, so the core clock steps are just 13 megahertz, which is huge. Because basically it means like this card could probably almost run 1332, because that's the next step up. Like, seriously, it's 1319. So currently it runs 1319 at like 1.33 volts, and when it was like less modded, it was 1306, and it can almost run 1332. But I think at this point it's just overheating. Though I guess I could still try. Well, the thing is, I've kind of run out of space. Right, like I've basically run out of space right behind the core, and I don't think actually doing anything, because the thing about the classified card, which is why I'm actually so surprised that this mod did anything at all, is that the classified has a very elaborate output filtering section right on the VRM, right? Like, just look at all of this. And then it's like, so I really didn't expect to achieve much, considering that this is what you have directly on the output, and just how many multi-layer ceramics are already behind the core. But what turns out that actually most of the ones that are there by stock are actually for the memory controller. They're not at all for vCore, which is, I guess, why why what I did was so effective. Because yeah, and here's like the front of the core. Like the output filtering for this VRM is awesome. So I'm really surprised that I achieved anything, because if it was like if it was like a crappy reference card, I would not be surprised whatsoever if you added a couple capacitors and picked up 10 megahertz or even 20 megahertz or more. But this is a classified 780 Ti, and it literally picked up a whole, at least 13 megahertz, maybe more if I bothered to test properly. Also, I will point out that these 1200 microfarad like capacitors over here, that's not really a reasonable place to put them in, because they're like, these are a low ESL variant. So these are Nichicon RS8 series, which is like Nichicon's low ESL capacitor, which basically means they work at higher frequencies than your bog standard aluminum polymer cans, but they still do not even like begin to compare to like the to say the SMD aluminum polymers that we have right here. Like this right here, that's a proper SMD aluminum polymer. And basically the advantage that these SMD ones have over the can types is just from the packaging. Just the fact that these are surface mount instead of with legs. And like the legs alone, like that length of extra, like that length of wire right there, that can easily add like, I'm not sure what the gauge on it is, but it might be like a milliohm of extra resistance to the capacitor. So that it's like, yeah, these are 7 milliohm ESR plus whatever extra wire length you add to it. So really not optimal. Maybe messing around with stacking more SMD polymers like this could be worth it. But the thing about soldering to these SMD polymers is that, especially behind the core, is that you need to do a ton of preheating. And it's just a pain, and there's not that much space behind the core on one of these to work in. So yeah, massive pain to attach even these guys, and getting creative with stacking SMD polymers, just like you can, but it's a pain. So I just kind of decided not to. And instead I spent a lot of time stacking multi-layer ceramics and just cramming them anywhere I could. So anyway, what I wanted to point out is you actually look at one of these cores here. And I have the multimeter out, so we're gonna have to zoom out some more. Oh boy, you guys can't see anything on there. Ta-da! So if we measure the resistance of the output of the core, up, we can see that. Damn it, this is gonna be really annoying. Okay, wait, I'm gonna put card like that, multimeter. Nope, that gives you glare. EMM like that, and now I'm not going to be able to read it. Great, I love this. But you guys can read it. That's what anybody cares about, right? So there we go. If we just measure across yeah, so 3.3 ohms. So that's a good, healthy resistance for a GPU core. The other card actually measures like 2.8 or 2.9, which is, that's just variance between the cores. Like some cards have slightly less, some cards have slightly more. Anyway, if we measure across the memory VRM to ground, so I'm just going to stab one of the display outputs, we get 80 ohms. So our memory chips have 80 ohms of resistance. Also, that includes like the memory controller and a whole bunch of other crap. Then if we measure from the PEX rail down there, we can see that it's like 0.7 kilo ohm or 0.8 kilo ohms. So anyway, that's that. And you'd assume that all of these, like if we look at the core, right, we have all of these very small multi-layer ceramic capacitors just sitting all around the GPU core. And you would assume that those are input filtering, like are bypass capacitors for the GPU core itself, right? Because they're very small, so they should be great for high frequency filtering. The GPU core runs at thousands of megahertz. A little over 1,000 megahertz. So it's going to be producing switching noise in that up to that frequency range. It would make sense to have some bypass capacitors sitting right next to the core with that kind of with just small capacitors jammed right up against the core to basically filter out the switching noise produced by the GPU core. Turns out most of those guys are actually for memory. Well, most of them are for memory, and some of them are for the PEX rail, which is just, to me, really surprising. Right? So, like, if we check this one, 80 ohms, and I'm just checking random ones. I'm not even choosing, like, specific ones. Like, you can choose literally anyone on there, and 80. Right? And if I go to the memory VRM over there, 0. Like, that's literally memory power freaking filtering, and it's basically all around the core, which is the part that really surprised me. So the thing is, I think the only reason why my mod... Wait. I'm not measuring any... Small little capacitors. I wasn't measuring... Yeah, see? Another one. Just memory bloody everywhere. So... Again, I have the probes touching. There, 80 again. So you get the idea. Basically, I would have assumed that would be all just filtering for core. But nope, it's all for the memory. So, and the similar situation on the actual back of the PCB. So if we flip it over, fold over some... There, so this way I'm not like putting stress on the PCB. And if we look at like, say... this row of little multi-layer ceramics right here, you would assume that those are V-core. But, okay, let's try to get an actual measurement for once. Yeah, that's PEX rail. It's not even the bloody memory controller, that's the PCIe rail. So, actually those might be PCIe connection, but... Anyways, so those aren't core. This big multi-layer ceramic right over here, if I could get through whatever thing, okay. There we go. Yeah, so that one's core. This big aluminum polymer, we could get a measurement. That one's core, obviously. So the big aluminum polymers, those are all core. And then, like, the multi-layer ceramics sort of in the center, most of those are actually GPU V-core. But the ones further on the outside are just all memory controller. So, like, all of the multi-layer ceramics that you actually have behind the GPU core, which to me it's really, like, why I find this so surprising is, like, if you look at the back of an AMD GPU and you measure a random capacitor, most of them are V-core. Like, most of the capacitors behind the core of an AMD GPU are V-core. Most of the capacitors behind here, just by quantity, I don't mean actual capacitance. If we go by actual capacitance, those aluminum polymers are 470 microfarads. They're so much larger than everything else in that area that, yes, the total capacitance for the core is much higher than everything else in the area, but just the number of capacitors doing the core is really, really low, which I found really surprising, and I assume is the main reason why I saw so much benefit from what I did, even on a card like a 780 Ti. Because the thing is, it's like, you're not going to really do much in terms of output filtering for the actual VRM. Like, it's a 14 phase. There's, probably one, like, out of all the GPUs out there, the output filtering section on this thing is quite elaborate compared to what you get on a lot of other cards. This VRM doesn't care. The fact that there's basically nothing behind the core is probably why my modification did anything whatsoever. And I've messed with, like, doing cap mods on AMD GPUs, and I've not really had anywhere near as much success as well here with this 780 Ti classified. So, yeah, I mean, that's, to me, it's kind of surprising, but it also kind of makes sense when you consider that, I probably more than doubled the capacitance available in the, like, small multi-layer ceramics. Because admittedly, I'm using, like, basically the multi-layer ceramics I'm going for are various sizes. So, and then I just go for, like, some of the highest capacitances I can find. So, like, for 0402, you can't, at least if you don't use, like, X6S, the temperature coefficient I go for is 105 degrees maximum temperature. Just because it's kind of like a nice, safe, pretty overkill actually for right behind a GPU core, but still. It just makes sure that, they can't fail. But the thing is just, yeah, like those are like 4.7 microfarads, and then the 0805s I use are 47s, whereas most 0805s that you find on actual PCBs they're usually 10. microfarads. So mine are like 4.7 times larger. So if I add a couple of so if you just count how many 0805s are here, there's like what do we have? We have 2, 5, 8. So there's like 8 0805s for the core in total. And if they're all 10s, then yeah, I more than doubled the capacitance in that package size. So yeah, there's really not that much, filtering directly behind the core, which is kind of surprising to me. But and it also does mean that the mod was far more successful than I was expecting. Like, I was expecting no benefit whatsoever. So 13 megahertz to me is a huge win. But anyway, so yeah, modding the adding multi-layer ceramic capacitors directly to the back of at least NVIDIA GPUs seems like a totally valid thing to do. I also want to experiment with actually stacking full-size aluminum polymers, but I will not be doing that on... I won't be doing anything to this card because I want to keep this thing just... Because the card's good. It's okay, even if I don't modify it in any way. And I'm just worried about the core dropping dead, and then I don't want to have to deal with the fact that the back of the core is all messed up by whatever I did. So when I try to replace the core or something. So yeah, that's kind of that on the modding these, but it does mean the thing is, going forward, it makes me much more excited to try mod some of the other NVIDIA much more. Well, I want to mess with this style of modding more on other cards now, because it's like, okay, I have at least one case where it worked. So it is it's a viable thing to do, and I should try it on more cards is definitely something I'm going to be doing. So yeah. Anyway, I guess since we have it taken apart, we may as well talk a little bit about the PCB. I mean the VRM on here, because we've kind of talked about the PCB a ton. So the thing about this VCore VRM is this is what I consider the standard standard EVGA classified VRM. It's a 14-phase. This is the version using a CHL8318. So if you compare it to a GTX 580 classified, which is the first classified to use this VRM, the difference there is that uses a CHL8228G. But this uses a CHL8318. It also uses IR35, what is it? Actually, let's check the notes. IR3598 dual drivers with doubling as a extra functionality, so you do get 14 phases. And then you have, IR60, yeah, so IR direct FETs, so the 6721 for your high side and the 6725 for the low side. The end result is that this, basically if you watch my GTX 580 classified video, then all of I literally just copy pasted my power consumption, VRM efficiency notes from there. But anyway, what it does mean is that 1.2 volts, 200 amps output at 300 kilohertz switching frequency on the VRM and 10 volts 10 volts drive, you're going to be looking at 200 amps output producing about 18 watts of heat. 1.2 volts, 300 amps output, 36 watts of heat on the VRM. And 1.6 volts, 400 amps output, 63 watts. 1.6 volts, 500 amps, 95 watts. Now, I also actually went and took some power consumption measurements while messing with these, because the reason why I basically decided to mess with these 780 Ti's is because I have a GTX Titan Z, and I want to mess with that GTX Titan Z, and my main concern with the Titan Z is that I would accidentally blow it up, because that's a reference NVIDIA card for a dual GPU. That's a reference dual GPU card. There's not a lot of space on those PCBs to do much of anything, and NVIDIA doesn't exactly the power circuitry, all the power management circuitry they have, and the very strict power limits they have a lot of the time, are heavily, in my opinion, for a long time, they were heavily motivated by the fact that if you exceed those power limits a lot, the PCBs can't survive it, even if the GPU cores can. So yeah, that's that's kind of not great. But basically, so with these 780 Ti's, part of the testing I was doing was also measuring how much power they pull while benchmarking them, because I don't want to accidentally, set the because I plan to just take the power limit off my Titan Z. I don't really care about having a power limit. I'll just take it off. And for safety purposes, I will just not raise the voltage too high. Because the thing is, your GPU core will only pull as much power as it needs, depending on what clock speed it's running and how much voltage you're running it at, and also what temperature it's at. If you can drop the temperature, you can run more clock speed at the same, like you can reduce your power consumption by lowering the operating temperature because it lowers your leakage, but it's not like you don't like cut your power consumption in, like you can get a significant drop. It really just depends on kind of the architecture that you're looking at, and so basically a lot of factors. So the temperature thing is just kind of a side note, which we will not consider. It's just like, okay, it's a thing, it happens, we will not worry about it because it's a mess. It varies from chip to chip. Just it's a thing though. So it's worth knowing that it exists. It's not worth like factoring in, because I like if you need the chip to be at a very specific temperature to not overload the power delivery, then you probably shouldn't be doing that. At least that's my outlook on it, because I do actually want to keep the Titan Z alive because it's expensive. And it's not the rare, like it shouldn't be particularly rare because it's a pretty popular like compute card as far as I know, but it is very expensive. So I do not want to break that thing. And so with these, I was monitoring the power consumption, and yeah, so well, let's just go through the notes. So well, actually, I'll show the monitoring setup I had, which wasn't really that complicated. I was just monitoring the power consumption on the. I forgot all these photos would be way... Oh, scaled the wrong thing. Great. Kind of forgot all these photos would be completely... Damn it. Completely out of scale. Ta-da! There. So, current clamp on the 8-pin power connectors, or the 12-volt lines of the 8-pin power connectors. So I'm not monitoring the power consumption through the PCIe slot, but I actually didn't remove the power limit on the PCIe slot. That's still there. I just removed the power limit on the 8 pins. So it's not like my mod disables the PCIe slot power limit. So I don't know how much it was pulling through the PCIe slot, but that was the test setup. And basically what the cards ended up pulling was so 1.2 volts, no overclock on the core, and plus 200 megahertz on the memory. You'd be looking at like 22.4 amps down the 8 pins. So not a lot of current, okay? So 1.2 volts, not really something concerning in terms of power consumption, because you'd be looking at like, just do the math, right? 22.4. I should have done this ahead of time. Too late. I'm not reshooting 30 minutes of video. So that's about 268 watts going into the 8-pin power connectors. So a good chunk of that is like, let's just assume all of that goes into the vCore VRM, which might actually be the case. I mean, we can try check. The thing is, there is some power balancing circuitry on even the cards as old as the 780 Ti, but yeah, I don't know how much it was used back in the day. It's just that there are some MOSFETs here, and fun fact, those power balancing MOSFETs have a tendency of blowing up as well. Like I've seen quite a few cards where it's just like this is literally adding failure points to your GPUs as far as I'm concerned, because I've seen, I think, a couple 980 Ti's and maybe some 980s where the only problem with the entire card is the blown power balancing MOSFETs. Now, it's possible that they just acted as fuses for something downstream of them. Like if the vCore VRM blew up and just, well, let's say one of the vCore VRM MOSFETs failed closed, but didn't get hot enough to like incinerate its surroundings, then yeah, one of these could have probably taken, like these are really low power MOSFETs, so these would have probably, if a large MOSFET fails after one of these, then these are probably actually going to blow up before the big MOSFET does. But anyway, so actually, yeah, because, well, let's see. Okay, it's not that one. Oh, we're in luck. There. So that phase is connected to this 8-pin, so we can just go through all of them. All right, so yeah, that one's connected there. Okay, so I'll go from the beginning again. Sorry, guys. Also, yeah, I think the entire V-core is probably just hooked up to the 8 pins, right? And then this one, yeah, this one has mega ohms, so we switch over to the other 8 pin, and bam! V-core, yep. And yep. And yep. And yeah, we'll call it. And also. Cool, awesome. So I didn't even realize that, but basically the power consumption, wait, so how many phases of the memory are on that? I'd assume none. I'd assume like the logical thing to do is just put your entire memory VRM on the PCIe slot, because that has a like 66 watt limit, and 384 bits of GDDR5 should not pull more than whatever that can provide. So, but just in case, I want to figure out which side of that is ground first. So this side's ground. Cool. So I assume this side's 12 volts. Yep, so those are connected together. And are these? Nope. Or... okay, so one of those phases is not connected to... well, I mean, we could try just directly from the MOSFET as well. That's actually really hard to probe. Wait. I think I got it. Yeah, okay, so that's directly from the MOSFET. Actually, I should be using the less messed up probe for that. There we go. And then this one... yeah, so that one's hooked up to something else. Is that one... that one has to be hooked up to an 8-pin then. Oh, yeah. That's exactly what it's hooked up to. So basically you have one phase of memory power hooked up to this 8-pin for no apparent reason, and then the other two memory phases are off of the PCIe slot. So that's what's going on with that. So, like, a third of the memory power might be going through, like, might be part of my measurement as well. So anyway, we'll just act like it's all core power only, because for the most part it should be. I mean, we have it's a third of the memory VRM. It's not going to change the results that much. So anyway, that was fun. So yeah, so 22 amps at 22.4 amps peak. That's Firestrike GT1 peak. So that's like 268 watts. If we divide that by 1.2 volts, that translates to about 224 amps. So, you know, there would have been, yeah, we would have probably been looking at like 200 amps output at that voltage. So, you know, 200 amps. Because there's obviously VRM power efficiency and there's VRM efficiency losses, and there's also the memory VRM included in that. So we'll just round that down to about 200. Now at 1.3 volts, no core overclock, the card pulled 28.5 amps peak. So quite the increase from just raising the voltage, but it gets worse once you actually start raising the core clocks, because fun fact, power consumption is linear with frequency and quadratic with voltage. There's like, well, that's like the very simplified, well, yeah, that's the simplified model for calculating power consumption for a lot of things. Like if you know the TDP, you know the operating voltage and the stock frequency, and assuming that the temperature doesn't change as you change your voltage and frequency, which is unrealistic, but if you just assume that you manage, like if you maintain temperature, you can scale up your power consumption by just doing quadratic for voltage and linear for frequency. And for the most part, it works almost perfectly. But anyway, so 28.5 amps at 1.3 volts, which translates to about 263 amps output on the VRM. So about 250. Right, we'll round it down again to around 250. And that's again just peak. That's not sustained. Sustained is like a couple amps lower. It's not much lower because I am just using the measurement from that current clamp, and it's not like super fast or anything. But it is you know, it is a bit lower for the average power consumption. The thing is, if that current clamp, like the way I look at it is, if that current draw peak is high enough for that current clamp to pick up on it, then it's probably high enough to blow up the VRM if that's an issue. So yeah. So anyway, so that's 1.3 volts, you know, just with only overclocked memory. And then going up to 1.4 volts, the card pulled 38 amps into like through the 8 pins. So 38.5 amps, and you know, times 12, that's 462 watts. If you divided that by 1.4, that's about 330 amps VRM output current. So you know, around 300 amps. So yes, there's a good reason for why this card has a 14 phase. Though it is worth noting that at 1.4 volts, the stock air cooler on this thing is just, it doesn't do any, like it's hopeless. You have no chance. But on water cooling, you could actually realistically like bench 1.4 volts just fine. That's not really a problem. So yeah, great thing that this has a strong VRM, because the thing is, once you actually add the extra core clock to that, so at 1.2 volts, but with 100 megahertz more core clock, the card actually pulled 24 amps instead of 22.4. So that's like almost a 2 amp increase from just raising the core clock. Now at 1.3 volts, I tested also plus 100, and I also tested plus 200 core clock. So at 1.3 volts, plus 100 is 31.5 amps, which, you know, that translates to about 378 watts. And all I did, like, if you didn't raise the core clock, it would have pulled 28.5. So, yeah, that's like plus 3 amps for 100 megahertz more core clock. You don't even need to change the voltage for that to happen. So, that's great. And so that translates to about, wait, really? 290 amps output? A 1.3? 31.5 times 12 divided by 1.3. Oh, damn. Yeah, that is actually 290 amps. Okay, so just by, oh no, so that's what, like, that's not even, that I think is like just under 12. That should be, yeah, that should be around 1200 megahertz core clock. So, whoa, that's a lot. That's like legitimately a lot of current, because the thing about the Titan Z VRM is that's a 5 phase with 60 amp power stages. So, oh boy, yeah, at 1.3 volts, it would actually probably be at risk of dying unless you do something pretty extreme to the cooling for the VRM. That is, well, I mean, I never expected to, well, I don't think the thing is, I do plan to keep the card on air cool. Well, no, I do want to water cool it eventually. Yeah, I guess we're not going to 1.3 volts because I actually really like having the card working. Anyway, but at 1.3 volts plus 200 megahertz on the core, so, you know, close to 1300 megahertz core clock at that point. So I think it's like 1280 on this card or 1290, somewhere around there. At that point, the card pulled 33 amps down the 8 pins, and that's still at 1.3 volts. So yeah, you know, 33 times 12 divided by 1.3, and you end up with a 304 amps output. So probably around 290 actual output current. Well, more like 280 maybe. So anyway, like, still doesn't matter. A lot, right? Like a lot. Getting close to 300 amps at that point. So that's concerning. But what's insane is at 1.4 volts, the card, if you do plus 200 on the core clock, you end up with 43.5 amps through the 8 pins, which is just like, yay. That's 522 watts through the 2 8 pins. Praise be to the lack of power limit on all of my cards. But yeah, if we divide that by 1.4, we end up with about 372 amps current output for the VRM. Now, again, part of that power consumption is the memory VRM. part of that power consumption is also the VRM itself. So it's not going to be actually 370 amps output, but it's probably still going to be well over 300. So yeah, 1.4 volts pushes a significant amount of current into the GPU core on these, which is not surprising. Like, this is a 28 nanometer freaking, monster die. And the stock voltage on these is actually normally like around 1.15 to 1.13 volts. So significantly lower than what you see on like a 290X. Like, stock 290X is... Actually, is it? I can't remember what a stock 290X is. I think it's around 1.2. So, yeah. Anyway, yeah, this thing pulls a lot of power. Now, I guess I could also go through some benchmark results. So, not with this card, obviously, because this card's actually quite inferior to the Zoidified one. And it's not because of all of the extra capacitors. Well, the capacitors make the disadvantage of this card even larger, but this card is just, I think, like 30 megahertz worse than the Zoidified card. And that's just because the GPU core itself is bad. So it was this much worse even before all of the modifications. So anyway, let's put that one out of the way and bring back this one. And we're going to go over some benchmark scores. Also, I need to put some standoffs into some of the screw holes so that I can put this thing, heatsink up on a desk, because currently those capacitors are a bit of a hazard with where they're located. So yeah, this thing, benchmark results. I actually did run a little bit of SLI. Let's see. Yeah, so I did run a little bit of SLI with the cards, which looked like that. I actually had 5 gigahertz going for that. Yay. Yeah, I was hoping to get some like easy high scores with these, but I didn't realize 780 Ti's were like, the funny thing about 780 Ti's is they're just like right outside of the area where the 7940X, because the funny thing about some benchmarks on Hardware Bot is there's a bunch of benchmarks where if you have a high core count CPU and the GPU is really old, you get a whole like, it's really easy to get a high ranking because the benchmark has a disproportionate weighting for the CPU score. But unfortunately, the 780 Ti's fall just outside of that category, where it's like they're not quite slow enough to benefit from a 7940X, and they're just fast enough to just actually need proper benchmarking. So I do need to actually run these cards on something other than air cooling at this point. And yeah, I don't currently have any liquid nitrogen, so I guess I'll have to... Well, I don't even really want to run liquid nitrogen on the card with the baked core. I'm thinking maybe dry ice. And the other thing I'm thinking is if I run dry ice is so much easier to handle that I could run GPUs on dry ice, CPU on dry ice at the same time. The main thing, because the thing is, if I run, like, I want to run these on X299, so with dry ice I can just fill up the, like, I don't have to do any temperature management. That's the thing, because these do have a cold bug. I already know that because I've messed around with them before, and they get kind of weird when you have them really, really cold. So yeah, I'm thinking, just throw them on dry ice. They should, like, the better one, I wouldn't be, like, I would hope that the Zoidified one does, like, 1500 core, and, well, actually, probably even more than that. Maybe even 1600. But I don't want to be, like, overly optimistic, because I already, like, the thing is, before I started messing with benching these, I was really optimistic about how good scores I could squeeze out of them because of the 7940X, and then I realized that wasn't really happening. So anyway, so here's the SLI score, and I did manage to get both of the cards to run 1303. That was with the Zoidified card was on the stock classified cooler, and the card with the baked core actually had the was on a Morpheus 2. So that one actually had a better heatsink, which was the only reason why I could even keep up with the one on the stock cooler, because that card needed so much voltage to finish Firestrike. So yeah, I think that card was at like 1.37 volts for that 1303 megahertz that it was running. Or actually, it wasn't even running 1303. It was running 1293. Yeah, so it was doing 1293 at like 40 millivolts more than the better of the two cards needs for 1306. and that's before all the cap mods. Now the voltage that it needs for 1319. So yeah. Anyway, that's the SLI score, and here we have the single card, which that's not too bad. Unfortunately, the combined score is graphic score is okay in that screenshot. CPU score is kind of low because I didn't want to bother with 5 gigahertz again. And I should have saved a profile, but I didn't because that's not a thing I do. I don't save profiles even when I should. So yeah, I didn't want to bother with 5 gigahertz on the CPU. So CPU score is a bit low because we are only at like 4.8. And combined score is a bit low because combined is a weird freaking test and it goes up and down at random. Like I ran another round of Firestrike after this where I slightly dropped the memory clock on the GPU, and my graphics score cratered. Like the problem is my GPU score dropped and combined went up. So yeah, I guess I need to just run the benchmark with like a bunch of, again, like I just need to run profiles again where right before the combined test runs, I drop the memory clock a little bit, which is a thing I already did on like 1080 Ti's as well, where it's just like, for some reason, if you run full memory clock on combined, it scores worse. So, yeah, but that's kind of been the adventures with the 780 Ti's recently. That's part of why, like, the thing is, I was really hoping to maybe like put up do a live stream with benching these in SLI, but like I was having so many issues with the BIOSes initially that I didn't ever get around to doing that. And then I just kind of modded this card, and at this point I've kind of done all the testing I want to do, came to the conclusion that I really need to get some better cooling for these, and yeah, that's kind of how we ended up with this horrible video right here, where it's almost an hour long. And by the time I shut up, it will be an hour long, because we all know me. But yeah, these were fun to mess with. Oh yeah, one thing I forgot to mention is the Probit header on these is the white balance is definitely off. Yeah, it's off. Okay, well, everything looks green. Thank you, camera, for nothing. I guess the green tinge is fitting for NVIDIA cards, right? So, anyway, yeah, the thing about the Probit connector is the vCore measurement from the Probit is actually like on the output of the vCore VRM. It's not at the core, because this reads really high. So that is something to keep in mind, is if you're checking the vCore with that, that's a totally different measurement location than what like this chip sees, and therefore what software sees. So yeah, that's also worth noting. And it's also I'm actually considering putting voltage voltage read wires onto the back of this card, but still that's a really, really minor thing to note. The good news is, like, the good thing about these cards, which is like about the classifieds, is that there's a piece of software called Classified Controller. And I'm not sure if you need like a specific version, but the version I have works great with these. So yeah, you get full voltage control. So you get PEX rail, memory rail, core rail. Now the thing is, both of my classifieds here is this one's SK Hynix memory. This one's also SK Hynix memory. And the thing about the SK Hynix GDDR5 is it clocks well. It does 2 gigahertz really, really easy. It just doesn't really scale with voltage. So yeah, I'm kind of just stuck with 2 gigahertz memory clock. This one doesn't even do 2 gigahertz. This one clocks a bit lower, I think. But yeah. So these do. So yeah, like the memory voltage control is kind of wasted because overvolting the high, like I tried messing with it, it just didn't go anywhere. Plus 50 millivolts and absolutely no gain in memory clock. So yeah, SK Hynix GDDR5 for everybody. Apparently the Samsung stuff scales, and I think Elpida also scales, but I'm not sure that any 780 Ti's have Elpida GDDR5, because I don't know that Elpida made GDDR5 in high enough clocks, like with a high enough speed spec to go onto a 780 Ti. Like these were using relatively top of the line GDDR5 memory chips at the time, because I think, what are they, like 1750 stock? So yeah, like there was a lot of, like, you could buy, there was a lot of memory chips that wouldn't do that kind of spec then, wouldn't do that at stock. So yeah. Anyway, that is it for the video. So thanks for watching. Like, share, subscribe. Leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, then I have a Patreon. There's also yeah, I have a Patreon. And then I also have there's also a Teespring where you can buy a bunch of sort of AHOC merch. There's shirts, there's posters, there's stickers, socks. There might be even more. I'm thinking about releasing some new shirt designs, though. The thing is, I don't want to have like a million different shirt designs. It just feels really cheap, if you know what I mean. It feels like, yeah, I don't know. But I guess, like, the thing is, if I do make enough designs, I guess everyone will find something that they like, but at the same time, it just feels really, I don't know, it feels really forced, right? It's just like, yeah, if you just spew out enough stuff, you'll eventually get everyone to buy something, and it's just like, I don't want to do that. That seems like, and at the same time, it's not like I don't put effort in the designs, but still, it's just weird, in my opinion, to have like a million different designs, but yeah. Whatever. That's it for the video. Thanks for watching, and goodbye. And I made it under an hour! Hell yeah!